We present a hierarchical controller for bipedal locomotion. 12 robot joints were controlled for this task. At the lower level of the hierarchical controller, an optimized central pattern generator network controls the individual joints. The pacemaker CPG generates the base signal of the network and is responsible for synchronizing the other CPGs. Each of the other 12 CPGs controls an individual joint. The target joint angles commanded by the CPGs forms the low-level control signal for the robot. To synchronize the robot's movements with the CPG network's output, a low-level feedback is used. Using this setup alone, the robot can walk, but since we used a robot model with structural asymmetry between the left and right legs, the robot always deviates to its left. Slippage on the ground also contributes to this undesired behavior. To handle this, we used a neural network as a high-level controller for modulating the overall movement of the robot. This controller monitors the state of the robot's torso and modulates the CPG network using only a two-dimensional high-level control signal. The neural network is able to handle both the structural asymmetry as well as slippage and make the robot walk straight. Using this setup, the high-level controller does not need to control every joint explicitly, thereby simplifying the training process. Here we show the result when the CPG network is used in isolation to make the robot walk. Although the walk is relatively stable, the robot does deviate quite strongly to the left of its walking direction. Over time, it ends up walking in an arc rather than in a straight line. To the left, we show the control setup in which only the CPG controller is used. We can see that the robot's deviation is significant. We also tested some linear controllers which tracked the current deviation and modulated the CPG network. The linear controllers perform better than the standalone CPG network, but still could not solve the deviation problem. Only when the neural network high-level controller was used with proper hyperparameter settings, the robot was able to eliminate its turning behavior and walk straight. This approach can also be extended to objectives such as balance control, but the presented results show the promise of this approach for achieving bipedal walking in uncertain environments.